So there was a blog post on Twitter with something that was interesting. Ben Lesh was showing some garbage collection stuff with async await versus promises. In particular, he was showing that when you have an async function here on the left, um, it was having different garbage collection semantics than promises and nested callbacks here on the right. So let's take a look at the code. The async function is pretty simple. It has a single scope, it does some awaiting, and then it goes. For the promise form, it does the same thing, but using .then instead of await. So there's a bunch of stuff going on with browser garbage collectors that is interesting, but it might be hard for somebody to understand what's going on without basically knowing a lot about how garbage collectors work, how browsers decide to garbage collect, and the DevTools to actually inspect this. So I wanted to make a little video to run down the differences of the different DevTools we can use to basically understand this ourselves and reproduce some behavior. Um, Doing so took a little longer than I hoped, but I made a little sandbox that you can go to, watch-the-gc.glitch.me. It's got a few examples, but they basically all follow the same workflow where it runs a function. Here we're running nested callbacks. And then it's got a constructor to construct a very big object. Here we save it in the callbacks big variable. And as it runs these callbacks, it does basically 4 steps that we do the same across all the different examples. In step 0, the initialization, for the most part, we just initialize our state. We create all the callbacks we need, and we allocate that big object. In step 1, what it does is it has this weird date.now thing to prevent browsers from eagerly statically analyzing that a variable is not going to be used, and then console log. This basically just makes it so that the browser doesn't eagerly, get rid of a variable. It's a little bit of a control step. For step 2, we don't actually do anything, but we know that there's no more reading of that variable in step 2. So when step 2 is over, when step 1 is over even, there's nothing that's going to read that variable anymore. Step 3, we actually go and we clear the variable. It is 100% safe to GC now. There's no reads, there's no writes to it. That variable has no reason to exist. And in step 4, we actually close out our total scope. That means that if you have any closures, they're also no longer holding on to that big variable. And we have these for a few different ones. We're going to take a look at the DevTools in, this is Microsoft Edge. It's Chromium based. So if you're using Chrome, it's the same DevTools. We're going to pop this open and take a look at some stuff. Let's pop it into a new window just so we can see things. You can kind of see there's multiple things going on here. For Chrome, they actually separate the different VMs and what they're doing. So you can see 2 here. One is kind of our test harness, our runner, and then the other is the worker. The worker is basically the thing that's actually going to run that function. If we go back to the page, you can see if we want to run that worker inside of a web worker, which means on a separate thread, we're not going to do that because while it's okay in Edge and Chromium, Chrome, all that, other browsers don't do well with heap snapshotting. And I'm not going to go into that here, but Suffice it to say, if you take a heap snapshot, you don't see what a web worker has if you're using anything besides Chrome right now, to my knowledge. Somebody can, of course, comment on this video and show me how to do it. I'd love to know, but I don't know how to do it right now. Maybe that'll be fixed in the future with some docs or something else. So the first thing, we automatically run step 0 in all this. It does a few checks here. And you can see the value has been allocated. In browsers that support it, we're actually trying to observe the garbage collection using a newer JavaScript feature called finalization registry. Finalization registry basically lets us add a callback that when the big value is garbage collected, we can update this and say it's been freed. But we're just going to take an initial heap snapshot. It's really what we care about. So the big is actually a class, and it's going to be under a class named EasyDefined. For some DevTools, it'll be easy to filter and find this. We can see it here in this filter view. Pretty nice. If we go and we open this up, we can see only one's been allocated. The class that opened it up is from here on line 46. Nice. This is what we expected. So we know it's been allocated, but what's holding on to it? So retainers. Retainers are going to be back references from an object to the root of the garbage collector. When we're talking about garbage collectors, in general, they work these days by whenever a garbage collection is performed, they crawl the garbage collection routes. These are objects that are alive forever, so things like the window on a browser, and they try to see what's accessible from that route, and it crawls that. Retainers are going to be kind of the back references. So if I had a variable at window.myVariable, the back reference is actually going to be that my variable path. So whatever the value is, let's say it was an array. If I was looking at the retainers view of that array, I would see my variable and it would go back to window. You can see that here. In easy find, we can see it's actually being held onto by a finalization registry. Importantly, you'll see that it's using a weak cell. So weak references, if you've used weak maps, weak sets, or weak refs now in JavaScript, you'll know that they don't keep an object alive. And so the finalization registry is holding onto this EasyDefined variable, but it's not keeping it alive. So we're going to close out that kind of path of retainers. And you'll see here, there's a callbacks big. That's the name of our variable in our code right here. So it's actually being kept alive by this this binding name. And if you really wanted to go, you could go and see what's keeping the binding alive. Well, it's being kept alive by some task. Task is being kept alive. This one is named tick4. It's actually being kept alive by a few of them. So when we go and we look at each of these tasks, tick 1, tick 2, tick 3, and tick 4. So here, all of these are back references. They don't necessarily keep it alive because sometimes you can figure out that an object is not used from a back reference. So that's kind of like what we're talking with the weak references. But this is kind of what we're able to make an experiment about and see actual data on what's keeping stuff alive. So this is just the end of the first tick. It was a lot to go through, but we're going to go through the other ticks a lot quicker. So end of step 1. So we have finished our little trick for the VM. So what happens if we garbage collect it? So you'll notice the size of the snapshots are around the same. So it's probably not garbage collected. So whenever you take a heap snapshot, it tries to do a garbage collection first. And so when you see the heap snapshots of the same size, probably means that no garbage was actually collected. We're going to go through and finish out step 2. We're going to take a snapshot. Still alive. So here's the big one. We're about to finish step 3. And when step 3 finishes, the binding is going to become null. And so if the JavaScript engine is able to garbage collect it at this point, then we'll actually see it reduce the memory usage in our heap snapshot. Oh, did I get it? Yeah. Finish step 3. So we're going to take one last one. And you'll see that it's reduced in memory usage a lot. And it's actually disappeared from here. So if we go back here to the last time it was alive, we're going to open this up. We're going to see what's keeping it alive. And so you'll see an interesting facet here. It's being kept alive, essentially, by both tick 3 and tick 4. This one's gone now, so we can't really see it. It's been garbage collected. But this one is still alive, so we can preview it still. So it wasn't actually kept alive by this. It was just in a context. So when we're going and we're looking at closures, although this scope exists and it doesn't directly reference callbacks big, there is a backwards path. And the backwards path is actually to the scope of this function. This outer function is referenceable from this inner function. But importantly, although the scope is referenceable, that actual binding is not. And so it's able to garbage collect. So like I said, we're going to do this in a couple of other browsers. They've got different tools with different pros and cons. So Firefox. Let's pop open Firefox for a second. We have the same thing. You'll notice here we can't detect free in this browser, so Firefox doesn't yet implement finalization registry. I believe they've done all the work, it's just not released out into stable yet. So when we go and we look at it, Firefox also has a memory tab. In Edge, I believe it was, memory here. We're going to go in Firefox and you'll notice something immediately. There's no way for me to see what's running in my harness, which is inside of an iframe, versus what's running in the main window. So this just takes a snapshot of whatever is on the main thread. And so we finished tick 0 here. So we're going to take a snapshot. It's around 12 megabytes. Good. So our big object is mostly consolidated arrays. It's 100,000 different arrays, and you'll see there are a lot of arrays here. Unfortunately for Firefox, we can't filter by class name very well. So we just got to kind of root around if we don't know what we're looking for. In the real world, generally you don't know what you're looking for. You're really looking at these counts, total bytes, that kind of stuff. But we have ways of figuring out what's holding on to stuff. So retaining paths, in order to get to it, you click on these 3 stars in Firefox. It's going to generate some nice stuff. So here, an array of, 100,000, it's pretty big on itself. So there's an interesting thing here. Retained size versus shallow size. This is present in all the dev tools if you know what you're looking for, but we should discuss what the difference in terms are. So, shallow size. Shallow size is the amount of memory it takes uh, to keep a single object alive, not including its children. So, keeping those 100,000 references to arrays is taking up a decent chunk of memory. Um, it's taking up 7% of our total memory. But if you look at retained size, it says 87% of our memory is being used. So, what is retained size? Retained size is a calculation which is basically if I were to get rid of this object, if all references to this object were garbage collected, and keep in mind there can be multiple. So if you have like window.a and window.b pointing to the same array, you'd have to garbage collect or null out both a and b in that case. If I were to garbage collect that, how much memory would I reclaim? So it's basically if I garbage collect this object, how much memory is able to be garbage collected in addition to it? How much memory is not kept alive by other things? So this is it. This is our huge honkin' array. Nice thing on the right here is you get a graph of things. You can see the garbage collector root here that we were talking about earlier. You can see instead of a tree view, you see this little graph view. Firefox will actually make graphs with, cycles and stuff like that while you're viewing, which can be better to understand what's going on than a tree view. But you can see it's actually kept alive. The property name of this is actually big on our class that we constructed. It's being kept alive by the callbacks big variable inside of a lexical environment. It's a function environment, this function, all the way back to the garbage collector root. Cool. So let's actually go and do a few steps. So we're going to do one step, the end of step 1 here. We finished our little trick on the VM. We're going to go to the end of step 2. No more reads remain, but the variable hasn't been nulled out. And then we're going to go to the end of step 3. This is after the variable has been nulled out. There, we see that it's able to garbage collect. Great. So we're going to move on to the next browser, Safari. Safari is a little bit interesting here. So what Safari does is it actually goes and has a timeline. And timelines are the only real way that you can get heap snapshots in Safari. And in order to get heap snapshots in Safari, you've got to edit this, make sure JavaScript allocations is clicked. There are some interesting things. Safari has a thing, console.takeHeapSnapshot, if you want to call it within your program. We're not going to use that right now. But in order to take heap snapshots, like I said, you must use the timeline view, and you have to be recording. If you are not recording, it's not going to actually take the snapshots in a way that you can see. So here we have it, Safari. It's the same thing. We've finished tick 0. It's allocated. So first thing we need to do, start recording. You'll see down here, it's got a snapshot. It's automatically going to take snapshots when it thinks it should. We're going to click next. It doesn't think it needs to take one. It took some after some automatic period of time. We're going to take one ourselves, and then we're going to do it a little bit faster. So step 2, step 3, step 4. That's our final step. And we're going to stop. So Safari. Let's go all the way back If I can, zoom out. There we go. You can kind of see where steps go on with the CPU usage. So here, you got a lot of arrays at the end of step 0, like we saw in the other ones. Still got a lot of arrays after step 1. After step 2, I believe that's right here, we still have arrays. So step 2 is over. This is where things get interesting. We're going to clear out callbacks big on the next step, which is, I believe, this little spike up here. So we're actually going to click the snapshot after that, and you'll see it's still alive. You'll see it's still alive, which is interesting. And the value is still allocated, right? But this is a trick. So we're actually going to go and we're going to start deleting heap snapshots because they're keeping stuff alive in Safari. So basically, the easiest way I've found to do this is to force garbage collection to happen. It doesn't always happen with Safari, which is a little weird. So we're going to force this garbage collection, hammer this little cycle button down there. Then we're going to take a snapshot, and then we're going to pause it. So here, it's still alive. So what is going on? Why is this kept alive? So Safari doesn't do exactly what the other browsers do. So if we go back to Edge, you remember this had no preview available? It's not available. In Safari, it's actually still available. If you take a heap snapshot of something, it's kept alive usually. And so we're going to actually run this again. Oh, and now it's freed because, of course, chose to actually do that. So if we go down here, why? Oh, because I'm not on the snapshot list. There we go. Sorry. Let's stop that. So it says it's freed. It's still being kept alive. Interesting. Yep. So this is being kept alive by a bunch of stuff. You can see this is being kept alive. It's referenced by internal objects. So, like I said, it's being kept alive by all these snapshots. Let's clear out the snapshots. They're all gone now. It's been freed according to everything except those snapshots keeping it alive. We're going to pause it. Still alive. Still kept alive by stuff. So the only solution I've found for this. The only solution I have found for this is basically to go and rerun the page without your DevTools. Get to the point you want, and then look at it. So we're going to do that. Okay? Clear off this, close out our DevTools for a little bit. We're going to refresh. We're only going to get to the end of step 3, and it's going to free in just a second. Go to our timeline. Go over here. It automatically takes some snapshots for us. And you'll see that the variable doesn't exist. So yeah, it's a little bit tricky with Safari. You can still get a lot of good information out of it, but you got to be careful with it. Don't take too many snapshots, really. If you want to see something be freed, you got to be careful. So that's it for this. Feel free to go play around. There's a few different examples, including a control. It's watch-the-gc.glitch.me. If you're interested in this kind of stuff, I'm Bradley Farias. I work at GoDaddy. We are hiring for people who are interested in enhancing our JavaScript tooling and infrastructure. So, yeah, let me know. Thank you. Bye.